Okay. This is an equation that defines a gas. All of the properties of a gas are encompassed in that equation. If I know any of the three variables that define a gas, I can solve for the fourth. For what we're dealing with in the future on next week, we're going to get back into doing stoichiometry involving gases, and now we have our moles. So we now can measure a gas, measure its physical properties, what's the pressure, what's the volume, what's the temperature. That then can be converted into moles, and we can then use a mole ratio, and we can figure out all kinds of different things. So this is a very important equation in that it defines a gas. This equation is different than the equation that we used yesterday, because this equation takes a gas under a certain condition, pressure, volume, and temperature, change two of the other conditions, and find out what the third property is after we've changed the environmental conditions for the gases. So the combined gas law will always involve problems that deal with pressure, volume, and temperatures at one particular scenario, and volume and temperatures at the other scenario, what's the new pressure? So it's like we're starting with the gas in one environmental condition, and we're ending with the gas in a new environmental condition. The ideal gas law deals with just a gas. We're not changing the conditions. We're not worried about manipulating the temperatures or the pressures. We're just asking now the question, all right, I've collected some gas, maybe in a chemical reaction. I know the temperature, the pressure, and the volume. How many moles is there? What is the moles? So the ideal gas law doesn't deal with varying conditions. It deals with a condition, all right? Okay, let's get ready to do some of the problems. One last thing before we move on. Take a look at this constant. It's given the letter R. I have no idea why it's given the letter R. But for this course, the gas constant is 8.314. You have that on your sheet, right, on that information sheet. So if you forget it, you can always go and get it. And you'll notice the units, liters times kilopascals over moles times Kelvin. These units are what make this number what it is. If we had different units in for these varying properties, if I had, say, torr in here and maybe meters cubed, that's got to be in Kelvin. But if I had different units up here, I'd have a different number in here. So this constant has its value because of the identity of these units. What I'm saying is, unlike the combined gas law, where you could use any pressure unit and any volume unit, for the ideal gas law, you must use kilopascals and you must use liters, and you always have to use Kelvin. And it's determined by this. All right, let's then solve some problems. You've got the sheet in front of you, no need to copy down. All we're doing is gathering numbers. I'm starting with the easiest of easy, hardly any conversions to do. All you got to do is put it in the equation. We'll work our way up to the harder ones where we've got to do some thinking in order to get the values. So don't wait for me. I'm simply going to start always by writing PV equals nRT, and I'm going to gather up some information. That first one is an N, 6.5 moles. The second one is a T, 25. And again, I'm hoping I've convinced you, as soon as you get a unit that isn't one of the ones that we can use, convert it right away. Don't let that bog you down in doing the question. In other words, hopefully we've done this enough that your skill is, you know exactly what that's going to be. What is 25 Kelvin, in terms of Kelvin? 298? 298 Kelvin. I have a P. I just recorded that. I have a value for the pressure, 120 kilopascals. And what am I looking for? It's the only thing missing. Oh, you guys are all busy doing the problem. Excellent. I'll let you continue. I'm looking for the volume. So PV equals nRT. I can put that information in. 120. Now, if you've done your units properly, I'm not worried about you putting the units in the equation. Next thing, V, N 6.5, R 8.314, and the T is 298. Now, for those of you who like to rearrange equations, that's great. But again, to just divide off the 120 and divide off the 120 actually is a time-saving move. I used to dislike this move. I used to rearrange the equation. But if you do it this way, you don't need to do a rewrite. You're just writing a few divisions, and now you just have to solve that problem, and you've got the V. This is actually quicker than a rearranging, I feel. Kristen, do you have a number? Ooh, 1.3 times 10 to the 2. Some scientific notation. That's exciting. For those of you who didn't put it in scientific notation, what's that, 130? 130 liters? That's exactly perfect. You did exactly what you were supposed to do. I've got two significant digits in my moles, which means it would be 130, which is a little ambiguous, and so the proper way is to put it into scientific notation. I would take this or this, right? This would be okay, but I'd give you a good old significant digits, question mark, minus a half or minus 1, something like that. Calculate the pressure exerted by 35.4 grams of oxygen gas at 30 degrees Celsius if it occupies 29 liters. Right off the top, you'll notice I give you a piece of information that isn't in PV equals nRT. I have 35.4 grams of O2. What do I need to turn that into? Moles. And what do I use to turn my mass to moles? Molar mass. All right, so now we've got to have all that good information that we've used in the past, and we just do it without thinking. What is the molar mass of oxygen gas? 32. Excellent. 32.0 grams per 1 mole. If you could do that without showing it, we're getting to the end of the course where you've used molar masses a lot. O2 is pretty easy to do in your head. You don't need to show all those little steps. How many moles is that? I need 3 significant digits. 1.106, 1.11 moles. Very good. That's N. T, 30 degrees Celsius. Again, I don't like that number, so right away I fix it. 303? 303. I've got a V, 29.0 liters. That's a good unit. So now we're ready to fill it in. Looking for pressure, volume, 29.0, N, 1.11, 8.314, and 303. Again, like I said, I've become a fan of dividing off those numbers on the side we want to get rid of, or multiplying. Divide it off on this side. Taylor, you got a number? 96.4. Looks like three significant digits. 96.4 unit. Yep, kilopascals. We got supporters on that? Excellent. I am moving quickly. I get the impression that I can move quickly. If I'm moving too fast, please ask me, all right? I'll really hold off on making fun of you if you do. I know many of you don't ask questions because you're afraid I'm going to make fun of you, and I am mean that way, I do. But really, if I am moving too fast, stop me. I won't make fun of you, I promise. Look, I'm not even crossing my fingers. Because this is pretty straightforward stuff, but if you're missing a step, it's important we get it. Okay. Again, I'm a fan of just writing down what I have. And if it's something that I can easily convert, great. And if it isn't, then I think about how I can get it into one of the units that I need. Temperature, 15 degrees Celsius. I will pause for someone's input. Who's got it? Sorry? 313? 313. $288. Yeah, 313 would have to be, yeah. Okay, that's okay. It's a good fix. Let's fix her. Sorry, what was that? 288? And next we've got this 790 torr, and I do need you to remember that that's a pressure unit, 790 torr. And now I need that conversion factor. And Jess has it because she was working on it miles ago. What do you got, Jess?
1 kilopascal over 760.
No, it's not 1 kilopascal over 760 torrs. Sorry? It's 101.3 kilopascals for every 760 torr. Remember at the beginning of the week we talked about pressure and how we had those different pressure units. Now on the back of your sheet, I didn't put torr because torr was given the unit in honor of his millimeters of mercury, of his tube of mercury. And because I didn't have enough room on that sheet, I couldn't fit it. So please don't write on it, but 760 millimeters of mercury is 760 torr. Actually, oh no, forget about it. I'll tell you that later. What do we have here for a value? If somebody has it. 105.3 kilopascals. Now, those are 3 significant digits, but let's assume that they're like 0.0 and 0.0, because really 4 is a good number of significant digits here. Now, my next bit of data is 5.63 times 10 to the 24 molecules. How do I turn individual molecules into moles? Yep. Yes. We use Avogadro's number, 1 mole over 6.02 times 10 to the 23. I had to take a look. Times 10 to the 23. And that's, we called that entities or particles or molecules. But this is, we've been using mole for quite some time. All these little things are going to come back into play here. How many moles is that when you get it? Jess?
9.35.
And that is N. So we've got T, we've got P, we've got N. We should be looking for V, and we are. So PV equals nRT. I'll rewrite it. Equals nRT. Pressure, 105.3. We're looking for V, 9.35. 8.314. 288, right? Divide off. Jess, what do you got?
112.6.
Liters, 3, 4, 3, 4. So probably better at 213. All right? On to the next one. A gas occupies a volume of 2.5 liters at STP. So here we're reminding you of those numbers for standard temperature and pressure. How many particles are present? All right. If they're looking for individual particles, I can't get that out of my equation, but what am I solving for first? Moles. I'm going to get moles, and then I'll do a Avogadro's number on it, right? So I'm looking for moles. I have the, now, SPP in that 3 letters is a temperature and a pressure. Yep. Yep, 273 Kelvin. Kilopascals. Excellent. Standard ambient temperature pressure was that room temperature pressure for a laboratory, 25 and 100, right? Okay, so we're solving. That's an ugly looking N. Looks like an H. Okay, Jess, you got an answer hand up there. What do you got?
Decimal 112 moles.
Supporters on that? All right. So now 0.112 moles. And now what goes where? Where does the big number go? On the top. 6.02 times 10 to the 23. Oops, that is particles in this case. You could call it entities. It doesn't matter. Molecules. We don't even know what the particles are. It doesn't matter. Per 1 mole, how many? Yeah, Jess? 22? And we'll just put particles. Now that's an important thing about gases. Notice in that question, nowhere in the question does it even mention what the particles are. These particles could be as simple as atoms, like the noble gases. This could be 2.5 liters of argon gas at STP. But this could be as complicated as something like an octane molecule, like if some gasoline evaporated and it was in a 2.5 liter container at STP. There would be the exact same number of particles in that container. That's the neat thing about gases. We've talked about solids and how we can take a mass and convert it into moles. And if we're dealing with a solid, we need to know exactly what the identity of the solid is, so we can get the molar mass and figure out the moles. We've talked about solutions, where we need the concentration. For that one, it doesn't matter what the substance is, but we need to know what the concentration is. We need to know who made the solution so we could figure out the moles. For gases, it's like the anonymous version of moles. We can figure out the moles in a gas and have no idea what the gas is. That's what's kind of weird and neat about gases. The properties of a gas are independent of the identity of the gas itself. If you think about that, that's really quite neat. That's one thing that we cannot get from these 4 properties of a gas. We can get pressures, temperatures, volumes, and moles, but we cannot get the identity of it. We don't know what it is. We need more information to figure out what it is. And that's kind of important. We'll talk about how that's important next week. And it's kind of neat. It's completely different than the solids and the solutions. Okay, one more problem. And where am I doing here? I'm going to here. Now, on your sheet, there needs to be a fix. I fixed it on the PowerPoint. It says 1.24 grams of a compound. On yours, it says moles. And that's a typo. Well, no, it's not a typo. It's a mistake. Yeah, I accidentally pressed M-O-L instead of G. It's not a typo. That's a mistake. Okay. At 100 degrees Celsius, a gas bulb with a volume of 284 milliliters contains 1.24 grams of a compound. We know the temperature, we know the volume, and we know the pressure because we get it to equalize to atmospheric pressure. And so from this information, and this information, T, V, and P, what can I get? I can get moles, right? It's what do we do with this mass is the question. You might thought, hey, we've converted mass to moles in a question earlier on. Let's do that. But if you read the question, nowhere does it tell you the identity of the substance. So you cannot convert it into moles because you don't know a molar mass. So we can't do that. So let's just keep that mass off to the side and let's just solve for moles. I've got a T, 100, which is 373 Kelvin. That's an easy one. I'll add that one up. We've got a volume. Now, what do I have to do with that? Change it to liters. I'm not even going to write down 284. I'm just going to move that over like we've been doing for our solutions. 284 liters. And I've got a pressure. 101 kilopascals. Seems to be only the 3 significant digits, but that's okay. Everything else is. PVNRT 101, 0.284, N 8.314, and what is that, 373? So you'll notice we're trying to do this problem. We don't even know where we're heading. But that's always a good plan when you encounter a question you're not sure what to do. Gather all the information up, and if you can solve for something, do it. It may lead you to a dead end. You might go, no, that's not going to be right. Let's go back and look at it again. But most often, we give you enough information to head down a path of steps. Get that information. 8.314. What do you got? Moles. A small number. Those of you who didn't use scientific notation, what do you got? 0.00925, correct? If you didn't use scientific notation? Did I do that right? 1, 2, 3? Moles. Okay. The question is asking for molar mass. And at this point, you should be going, I can't get molar mass. I don't know what the substance is. The molar mass is my conversion factor. How am I going to get molar mass? Scott, do you have a suggestion? And why would you do grams divided by moles? It's absolutely correct. Just take your grams and divide it by moles. This is what Scott did. He thought about how we convert grams into moles. And he remembers that we write down our grams and then we always multiply it by a conversion factor that is 1 over molar mass. And that gets moles, right? That's what he thought of. He thought of our conversion factors. So then he simply rearranged this and the molar mass came up there and the moles went down on the bottom. And so he's doing grams divided by moles. That's an excellent way of doing it. I wouldn't have done it that complicated. There's a much easier way. The unit for molar mass is grams per mole. And so if we have a gas where we know how many grams there are and how many moles there are, then why don't we just divide it so we force it into a unit of grams per mole? That's exactly perfect. That's the way I would do it. Now, a third way of thinking of it, molar mass is a conversion factor. We've had to solve for conversion factors before. in the solutions unit, what's the conversion factor we had to solve for sometimes when we were doing stoichiometry in the solutions unit? What conversion factor were we finding sometimes? Yeah, the concentration, right? That's a conversion factor. And I always said to you, when it asks you for the conversion factor for concentration, write down C equals N over V. Well, molar mass is a conversion factor. And molar mass's equivalent conversion factor is molar mass is grams over moles. So you take your mass and divide it by moles, and that's your conversion factor. Either way, it doesn't matter. I'm just going to take this little thing here, grams per mole, and I'm going to just put 1.24 grams, and I'm going to divide it by 0.00925 moles, and I'm going to erase this. And I'm going to get a molar mass of, yep, 134. 3 significant digits. Looks good. 134 grams per mole. Sound good? So don't forget, if you're asked for a molar mass and you're given grams and moles, just divide them off. Force it into a unit of grams per mole. Okay. You have piles of questions on this. You'll notice I've given you a page that has half a page of problems, also textbook problems. When it comes to gases, the ideal gas law is your conversion factor, molar mass, concentration, except it's a big, long equation and we need some extra information to work with it. But that's what it is. This is getting the properties of a gas and turning them into moles, or moles into a particular property of a gas. It is the conversion factor for gases. So when you get a question that involves a gas, you are automatically thinking, just like molar mass, and just like C equals N over V, you're thinking PV equals nRT. That is the last indoctrination that you need. That's why we have you do a whole bunch of them. All right? Okay.